all scales. Starting with galaxies, we're used to looking at these kind of rotation curves for spiral galaxies, where if you look at the velocity as a function of radius, the observed rotation curves do not match what you would expect from the luminous component. So this suggests that there is some dark component that contributes in addition to the luminous component to give what we see. Moving on from galaxies to galaxy clusters, we observe dark matter in a variety of ways in galaxy clusters. So just using virial theorem, you can observe a cluster of galaxies and look at the relative motion of the galaxies and compute a virial radii and masses and see what the actual mass of these galaxies are. Another way to do this is actually to look at the X-ray gas that comes from these galaxies. And it turns out that when you look at the temperature of the gas in these galaxies, it does not match the observed optical mass. And so we see that there's possibly a missing component in that kind of analysis too. Gravitational lensing, these are popular pictures. So in this particular case, we see that there's a galaxy cluster that is lensing faraway galaxies in the background, and you see these kinds of arcs, and you can compute the masses again over here for these galaxy clusters, and they're not what we expect. So there's once again some missing component. And obviously we've all seen these kinds of pictures of the bullet cluster where we see two post-collision galaxy clusters. They've gone through each other, except that the baryonic component, or the part that is not dark, as is seen over here through X-ray, actually you see a shock wave front, and the blue parts over here are gravitationally lensed dark matter. And so you see that collisionlessly the dark matter has gone through, whereas the baryonic matter, which interacts with itself, stays behind. On the larger scales, we have cosmology, and cosmology tells us, gives us this wonderful picture in which we see that most of the universe is actually this thing called dark energy, and the component that is matter is not actually entirely baryonic matter. So there's this missing component that is 23% dark matter. We constrain the amount of baryonic matter through a variety of techniques. The most popular is looking at Big Bang nucleosynthesis and realizing that we need the baryonic fraction in the universe to be in a certain region so that we get the correct abundance of the light elements. And also it's important to note that dark matter is required to seed structure formation. If we look at the structure in the universe today and scale and go back in time and say when structure formation should have started, we realize that we need gravitational wells that cannot be provided by baryonic matter, because it's still free streaming at that time. So dark matter actually provides the gravitational wells that attract the baryonic matter and seed the structure formation process. And actually for that reason we need dark matter to be cold as well. Otherwise it would just be free streaming at the time when we need structure formation to start. Okay, so we see that there's dark matter. So now we would like to look at some candidates, and there are many out there. There's an entire particle zoo suggested by scientists. I will be focusing on WIMPs, weakly interacting massive particles. And so we can paint a picture in which early in the universe we thermally produce some kind of particles that are massive. And so early on they're in thermal equilibrium. When the universe starts expanding, eventually the temperature of the universe drops below the mass range of these particles, we stop creating them, but the annihilation continues. And then in this kind of universe, if we come to a point where the Hubble expansion is faster than the rate of annihilation of these particles, we freeze them out. The WIMP miracle is the fact that if we require this relic density to correspond to the amount of dark matter that we see in the universe right now, we automatically come to weak scale physics. So the cosmology suggests that we should be looking at weak scale cross sections and masses for dark matter, and this is why the WIMP model is very attractive. So okay, the weak scale. Is there something at the weak scale in physics? Oh yes, there is. So we know that there are problems with standard model. There are issues such as gauge hierarchy. We know that coupling unification doesn't really go to a scale and unify. It actually, all the couplings kind of miss each other. And we have questions about electroweak symmetry breaking, why that kind of stuff happens. And so there are a lot of physics models that have been suggested to deal with these kinds of physics problems. And it turns out that in some of those models, we produce particles, and over here I mentioned LSP and LKP, the lightest SUSY particle and lightest Kaluza-Klein particle, as good candidates for dark matter. So in cosmology, we're looking for something at the weak scale. It turns out that there are models in place in physics that, in order to try to solve physics problems, give us good dark matter candidates. So okay, so WIMPs are a good model. How do we find them? So we can try to look for them indirectly, so look for their annihilation signatures out in the galaxy, or we could try to look for missing energy in colliders by trying to produce these particles, or we could do what I do, which is try to directly detect them in terrestrial detectors. So okay, so continuing forward, I will focus on direct detection. How do we do direct detection? Okay, so we want to start with certain ideas. We have an idea of what the annihilation cross-section might look like, and that gives us some clues about how WIMPs might interact with quarks or with baryonic matter. So that's good. We have kind of an area to look for, some kind of interaction cross-section. Now we make a few more assumptions. So we assume that our galaxy sits in a large halo of dark matter, and that this assumption is actually not very far from the truth. So we're located somewhere in the Milky Way, about 3/8 of the way out, and so for this isothermal dark matter halo, we can set up this kind of model where we see the dark matter particles coming at us in sort of a WIMP wind, if you will. Okay, it has a Maxwell distribution, maximum Boltzmann distribution, with a characteristic velocity around 200 to 300 kilometers per second. Now this guy, combined with this, which is our estimate for the local dark matter density, is now starting to give us enough information to think about the kinematics of how an interaction might occur in a detector. Okay, so we have these dark matter particles coming in, and they're pretty slow, right? We've said over here that their characteristic velocities are about 200 to 300 kilometers per second, so they're not relativistic, and so we actually see, we might be able to see coherent collisions with nuclei in terrestrial detectors. And there is an enhancement of this cross-section because the individual components from the nucleons add coherently. And so now, just hand-wavingly, we can write down this kind of expression, and so we know what kind of recoil energies we might look for. And so this is what we get. This is the differential event rate as a function of energy. So this is just the cartoon version, and in reality, when you plug in some numbers, you get this kind of thing where we expect recoil energies with characteristic energies of around 30 keV, so in the tens of keV, and you can see that these event rates are pretty small. So let's pick up any of these materials. Actually, let's say germanium. And so in this range over here, we're seeing a fraction of an event per kilogram per day, right? So this is a rare event search, very, very low event rate. Most of the materials we could even think of building detectors with have much higher radioactivity rates than this. So there are certainly a lot of challenges that are presented. Low energy thresholds, just from the previous plot you saw that we're talking about tens of keV of energy. But while building an experiment, we want to control our background, try to maintain radio purity. we can take advantage of one interesting thing, which is that we can possibly discriminate between nuclear recoils and electron recoils. Now, WIMPs should scatter off nuclei, whereas electromagnetic interactions happen with the photons, with the electrons around these atoms. So if we can somehow discriminate between nuclear recoils and electron recoils, we can afford to have some amount of electromagnetic background as long as we can reject it, right? Though of course neutrons also create nuclear recoils in detectors, so that's one source of background that we want to tightly control. And so you have to set up these experiments deep underground so that you can reduce the cosmogenic neutron contribution, which is just muons coming in, interacting in materials around you, and producing neutrons that can go into your detector and create nuclear recoils. Okay, so, and of course, we want to have large target masses, and we want to have long stable running times so that we maximize the exposure of WIMPs to our detectors. Okay, so keeping these things in mind, there's still a couple of ways we can go about setting up an experiment. We could try to do event-by-event identification of nuclear recoils by requiring that in your entire experimental setup, an event that comes in and tracks once is a more natural candidate for being a WIMP than something that comes and tracks twice, because we know that these are very low interaction cross sections. And we're looking for nuclear recoil, so nuclear recoil versus electron recoil discrimination, this kind of thing will be helpful. So that's how you can do event-by-event discrimination. Alternatively, you can just try to suppress your backgrounds really well and not care about any of these things and just look for what's called either an annual modulation signal, which is just a solar system, the motion of the solar system, or the motion of the Earth around the sun creates a change in the flux, the incoming flux of WIMPs as we would observe them in a terrestrial detector. Alternatively, you could look for a direction modulation as the Earth spins about its own axis. And of course, for this kind of thing, we'd first need to detect WIMPs, and then you'd build a detector large enough, and you could probably set up a diurnal direction detector. But anyway, so we focus on this strategy. That's what CDMS does. An example of this is Dama Libra, and there are actually some collaborations that are doing some great R&D work on diurnal detection as well. Okay, so this is what CDMS is in a nutshell. We use germanium and silicon target masses. We control backgrounds by going deep underground using clean materials, shielding, and we do event-by-event discrimination for whatever background we have left by utilizing ionization and phonon signals. So for every event, we record the ionization signal, which is the amount of charge you shake up in your detector during an interaction, and the phonon signal, which is the amount of recoil energy created vibration that you're setting up in your detector. And by looking at those two things, it turns out that if you put them on these two axes, you naturally separate out your background, your electron recoil background from your nuclear recoil signal. And finally, the important thing is setting your expected background in a way that maximizes your discovery potential. And I'll be talking about all of these things in detail. Okay, so let's look at the detectors a little closely. So our detectors are essentially little hockey pucks of germanium and silicon, weighing 230 grams, 110 grams for germanium and silicon individually. And they are stacked in towers like this and operated at 40 millikelvin. I will go into details of why the temperature and whatnot, but anyway, so the basic principle is this is a schematic for a detector. We pattern superconducting thin film phonon sensors on one surface. They're divided into 4 quadrants, and that helps us with position construction. So you image using 4 channels. And across this detector, we set up a field by just biasing it. And the bottom electrode over here is divided into 2 regions so that we can set up a fiducial volume. So events that occur in the outer ring can be rejected by using this charge fiducial cut. So the charge readout is actually fairly simple. This is simple ionization readout technology. The phonon measurement is interesting, so I'll talk a little more about that quickly. So okay, zooming in on one of the detectors, this is what you see. So this is the patterning I was talking about. And what we have, here's a schematic of what's going on over here. So this is a crystal, this is a germanium or silicon crystal in which your particle comes in and interacts. It generates phonons. The phonons are collected in this aluminum collector. This is all superconducting, which is why we operate at low temperatures. And what happens is these phonons break the Cooper pairs, the superconducting Cooper pairs. These particles diffuse and enter a transition edge sensor, which is rigged up in a way that it sits on its superconducting transition edge. And so what happens is when you have energy dumped in here, you change the resistance of the system. So you're writing this curve over here, and by changing the temperature over here, you're changing the resistance. And that can be read out if you set up the right kind of circuit. And the way we do that is this sits in series with an induction coil, and that is read out by essentially what's a very, very tiny magnetometer. And so in this scheme, when you have interactions happen over here, you go through this entire chain and read out a signal in the phonon. Okay, 4 channels. I wanted to come back to this quickly. The 4 channels give us position information. So the idea is that if you have 4 quadrants, you can look at the relative amplitude of the pulses in each of the quadrants and get partition information. And you can look at the relative arrival times and construct another XY metric using that. So here what we've done is we have a collimated source, and so this is a plate with holes in it, and you have a source, and you see you can image the location of the sources. And over here is a partition information, which is based on just the relative pulse amplitudes, and this is the timing information. So that's constructing your position based on the pulse arrival time. Okay, so now we've seen the basic the phonon and ionization operation. So how do we do discrimination with this? Okay, so what I was talking about earlier, by reading out the phonon and the charge, we can separate out the electromagnetic background from the nuclear recoil signal. Now, instead of just putting charge on the vertical axis, what we can do is we can construct this parameter called yield, which is charge divided by the phonon. Okay, so this cartoon over here turns into this. Now this is calibration data, so we can stick a barium source next to a detector and create photons and electrons, and they show up around yield of 1 on this plot. And by sticking a californium source, really putting in neutrons into the detector, we see that the nuclear recoils have suppressed ionization yield, and they show up over here. Okay, but there's a problem, and you might have already noticed this. There's this rain over here of photons and electrons that's raining down, and it's starting to even enter the signal region. So this would be where we would see WIMPs. Okay. And what ends up happening is this is caused by events that happen within the first 10 microns of the detector surfaces. What happens over there is we have poor charge collection. So when the charge is suppressed, your ionization yield droops, and you'll end up having all these surface events, or these events that have suppressed ionization yield. So these are primarily caused by electrons, X-rays, and low energy gammas from contamination on or around the detector surfaces. And so if there's a way to minimize this contamination, we would see less of this. But we can actually go ahead and still discriminate against these events. And before we get to that, let me quickly mention that just using this ionization yield scheme, we have a gamma rejection of about 10,000 to 1, and pretty crappy surface electron rejection. It's only 10 to 1. But okay, so how do we actually reject these surface events? So the cool thing about the phonons is the arrival times are different for these different kinds of events. Surface events are closer to the surface, arrive faster, and so the pulses are faster. A nuclear recoil is in the bulk of the detector, and so has a slower pulse. And using this timing parameter, you can discriminate against surface events. So once again, over here, this is just a simple discrimination plot. Using the surface events from the barium calibration source and using neutrons from the californium source, we can construct, we can set a cut on this timing parameter over here. And we can set it in a manner that we require a certain amount, we do not allow more than a certain amount of background. Okay, so this is what the combined rejection looks like. So over here on the vertical axis I've left ionization yield up, and then on the horizontal axis I've put this timing parameter that we just saw in the previous plot. So the bulk gammas were being pretty well rejected anyway by ionization yield. Now you had these surface electrons that were drooping down into the signal region, except using this timing parameter we can exclude them and define this box over here as a signal region. Now all of this is again from calibration data. This is not WIMPs obviously, otherwise you would have heard. So now combining the ionization yield and the timing parameter, this is the kind of rejection we have: 10 to the 6 to 1 for bulk gammas, and for surface events 1,000 to 1, which is a lot better than 10 to 1, right? And so these are the residual rates we're left with. So this kind of sets the scale for what kind of rate we can count to in WIMPs, right? Okay. Okay, so let's now talk about CDMS-II and the setup at Sudan. So we take all these detectors, we build towers out of them, and we toss them into an experiment deep underground at the Sudan Underground Lab, which is in Minnesota. So by going underground, we're suppressing our muon flux, right? So we go deep underground, we build a nice clean room, shielded clean room, and inside there, we start tossing detectors into this can. So let me use a schematic to explain what's going on over here. So this is the innermost sanctum. This is where we would put detectors. And this is what we call the ice box. It is connected to this dilution fridge, which you see in the background, this blue tower over there. Okay, now, so outside this can, we have several layers of shielding because we need to shield against gammas and any cosmogenic radiogenic neutrons. So we start off with some poly. Then you have some ancient lead, which has low radioactivity. Then you have regular lead. Ancient lead is a lot more expensive. That's why there's a thinner layer of it. And then you go to the outermost poly. The poly moderates neutrons, and the lead kills gammas. On the outside of this now, we have these scintillator, so active scintillator veto to reject muons. So we're deep underground, but any muons that are coming in, we want to be able to tag and reject any events caused in coincidence with those. So okay, that's how these are the layers of the onion, if you will. And on the side over here is where we read out signal. So there are wires going in, strip lines and stuff, and I'll show you the inside over here. So inside the ice box, you have these towers. This is just a schematic. I couldn't actually find a good picture of a tower. But you have the cold electronics that sits at the top, and this is what you're seeing over here. This is the top view. And so the detectors are on the inside, so behind this layer of copper over here. I should also note, of course, that all the detectors are housed in very clean copper containers, essentially. Okay, so we had 30 detectors that ran in Sudan between 2006 and 2009 with just about 5 kilograms of germanium and about 1 kilogram of silicon. Okay, and how do we do with all of this? This is what we've had in the past. These are the results from the past. That blue line over there is the earliest CDMS-II operational results with just 2 towers of detectors. Each tower has 6 detectors in it. Then we added more. We did cryo upgrades, and we added the full complement of detectors, which was then 30 detectors total. And this was our result in 2009. So that was just from that particular exposure, and then combining it with all CDMS results gave us that. And so now, doing this analysis, we had an expectation that we would move down further on this plot. And so what you're seeing over here is this is how we report results by saying how much cross-section we've excluded to 90% confidence against this WIMP mass. So cross-section versus WIMP mass is kind of the metric in the field for progress. Okay. So, yeah.
What are the shaded areas in the plot?
Yeah, sorry, I should quickly mention that too. Those are theoretically favored areas. So different models over here. There are some supersymmetric models. And this, I think it's mostly SUSY over here. So yeah, and actually this continues like way down. we're just starting to graze the top of it. Yeah, thanks for pointing that out. Okay, continued operation. So after that result, we continued taking data. The setup itself had no changes, but we had the chance to perform some analysis upgrades, and so I mainly categorized them into data pipeline kind of things that were upgraded, and improved background modeling and better background rejection. So mostly it was more streamlined and automated software to deal with large amounts of data. A lot of automated quality checks. I think we realized in the last analysis that we spent a lot of time individually picking out data sets and throwing them away. So we have some nice tools that automatically do KS tests, monitor neutralization, and throw away data sets that we would reject ourselves. And improve background modeling, and I'll talk about that a little later. So this was a previous run which resulted in the PRL. That was about 400 kilogram days of data, and so now we have 600 kilogram days of raw data in this particular result. So let me spend some time on the analysis pipeline. We get raw data. There's WIMP data, and then there's barium calibration data, which the quantity of the barium calibration data is 20 times our exposure in WIMP. We go through, reduce pulses, calibrate energy. We do a blind analysis, so we have to blind the WIMP search data once we have our calibration and stuff in place. Apply some data quality. This is mostly done automatically anyway. We just make sure all of it is consistent. And then we do something called a position energy correction, and I'll come to this later. This is, I guess, this is something you would do in any kind of imaging experiment, because there are some dependencies of your parameters in position and energy. So once you have this corrected data, you can apply your physics cuts and do your estimates and freeze your analysis and go ahead and unblind. Anyway, okay, so let's walk through those steps. Okay, data reduction. This is kind of the standard stuff. You take your pulses, you optimal filter them. So if you know what your noise looks like, you can de-weight that noise essentially, and fit pulses. And so if you have a nice pulse, you can then go ahead and make measurements on it. Things we care about, like timing parameters or the amplitude of the pulse. And so this way you've reduced terabytes and terabytes of data to just gigabytes. Okay, then for energy calibration, I told you we were taking a lot of that barium data. So that barium data has lines at high energy, so this is in the 300 to 400 keV range. So using the lines, we set the total energy scale. Then we go back and look at the low energy scale by looking at an activation line in germanium in the WIMP search data. Okay, and so that just helps us confirm that our energy readout is linear, right? And so once we've calibrated the charge, we can use the charge to calibrate the phonons. And so that's how you do the energy calibration. Okay, now blinding the data. This is important. We want to mask our signal-like events to avoid statistical bias. So we don't want to set our cuts on the data from which we want to make a discovery, hopefully. And so we overblind, in fact, because when our initial physics cuts and stuff are not set, we kind of guesstimate for what single scatters look like, what the nuclear recoil band is, and blind a large swath of WIMP search data. Okay, so then we go ahead and set cuts mostly on calibration data or on independent event distributions, meaning that if we're looking at WIMP search data, we're looking always outside of the WIMP search area, and we break this quarantine, meaning we unblind only when the entire analysis is frozen. And that's when we see whether we have any events or not. Okay. Data quality, I was telling you this is all automated stuff, and essentially you can see what the effect is. So this is a plot of time versus the exposure. This section over here is this analysis. There are breaks in between for cryogenic maintenance, but mostly what you see is that this line shows you what the data recorded was. We exclude some sections of data because of poor detector performance, and then this is what we land up with, which is the actual exposure, which was 612 raw kilogram days. Okay, data quality is in place. We've thrown away bad data, so now we can do position energy correction. So now what is this? Okay, so the basic principle is that the phonon pulse shape varies in our detectors with position and energy. Normally we wouldn't care, but this is bad because the scale of this variation washes out all discrimination we have between nuclear recoils and surface events. So that's bad. But it's easy to fix. We take all that calibration data and we essentially map out our detector in different observables, in different position observables. So this is 3 parameters we've used over here, and you'll end up with this weird bowl. And the problem with this bowl is it's showing you different colors. Using a very thin spread of energy of gammas, this should look roughly the same is the idea. Okay? A cross section of this, a slice of this would look like this. So just imagine slicing through this bowl, and you get this shrimp kind of shape. And over here I have the partition-based radius, so that was the relative energy, and this is the relative timing-based radius. And you see that there's a degeneracy which can't be broken unless you use a combination of these two guys, which is that you read radius by walking across the shrimp and following it, following the body of the shrimp. And so this is the outermost region, and this is the innermost region of the detector. And the color is giving you the timing scale, and as I was mentioning, this variation over here in timing is enough to wash out discrimination against nuclear recoils. But anyway, once you've characterized the detector and you know how it behaves in the volume of the detector, we can just go ahead and correct all this variation out. And so we developed lookup tables that in this parameter space tell you what the characteristic pulse shape over there looks like, and then you just go ahead and correct it in your WIM search data and all the remaining calibration data. So, okay, once we have that, we can actually do some physics. We can set physics cuts, and essentially our WIM search selection will consist of this. So we have an energy threshold cut, so 10 to 100 keV. That's the interesting region of recoils that we want to look at. veto anti-coincident, we don't want any activity in the muon veto. Single scatter, and that's just saying that WIMPs will not interact in your detectors more than once. There was this charged fiducial volume I talked about, so that's just rejecting events on the outside of your detector, or in the outer rim of your detector. There's a nuclear recoil band. Obviously, we're interested in nuclear recoils, and the phonon timing. And so what you see on this plot is how the efficiency looks like at different stages. So this is when you start off with data quality. You're in the 90s%. Then you apply a nuclear recoil cut. You apply a fiducial volume cut, and by the time you apply your timing cut, you're looking at about 30% efficiency. Yeah?
Why is there an energy variation?
Well, that has to do with like different kinds of things, but like in essence, over here, you're measuring it poorly also to a certain extent towards the outside. And then the fiducial volume, there's some interesting effects that need to be corrected because we use neutrons. We use neutrons as a proxy for WIMPs, but neutrons can also multiply scatter inside our detector. So there are several things like that go into it, and that's why you get that shape. Okay, now this is an interesting point, which is choosing our background. People typically ask us, well, so you have this much background in your detector, so are you kind of stuck with that situation? How do you do better? And really the simple answer is you cut harder, right? But what we're essentially trying to do is set our timing cuts and our yield cuts and such in a way that maximizes the science. So our goal is essentially to select a surface event cut that maximizes our sensitivity. And so we want some kind of automated routine that says, well, okay, this is how much science I can get out of the detector by varying the cuts this way, so let's do that. And in this plot we see what that means. So we can model our sensitivity as a function of expected leakage, and we notice that there is a sweet spot over here. So ideally we want to limit our background to about in the 0.5 to 1 background surface event range, and that actually gives us the best reach. So over here on the vertical axis is what the limit would look like for this expected leakage. Okay. Once we've set the cuts, we can start estimating our backgrounds and stuff. We need good background models, so this is how we do it. We have our cuts in place, and so now we can see the contribution of surface events by measuring a pass-fail ratio on any kind of sideband that we have. Okay, so we measure this pass-fail ratio and multiply it by the number of events that fail the timing cut, and that gives us an estimate for what kind of surface event leakage we would expect. So now we can estimate this pass-fail ratio for our timing or surface event cut using 3 different ways. In the WIM search data, here's a nuclear recoil band, and this is a cartoon, so don't worry about not being able to resolve what's going on over here, but you see the nuclear recoil band over here. In the nuclear recoil bands, the singles are blinded, but the multiples are available to us to do some kind of estimation of this cut performance. So you can look at the multiple scatters inside the nuclear recoil band. In this region right outside the nuclear recoil band, we can look at multiple scatters as well. And we can also look at single scatters. And then we can use the calibration data, and we can assess both inside and outside the nuclear recoil band what this cut performance is. Now, these methods 2 and 3 require a little bit of systematic correction because the distribution of events that we see over here is slightly different from the distribution of events we see over here. And so there are some performance dependencies. So let me rephrase that. So the fact that the distributions are different over here mean that the rejection will be different in the 2 cases. And so we apply a correction factor that then gives us this right expected leakage. Okay. The neutrons also go through a similar process, except that here we're estimating our radiogenics and cosmogenics separately. The radiogenics is just counting the materials, so we know what the contamination on the materials is. We put that into a simulation, and we see that the contribution is actually much smaller than the surface event background. For the cosmogenics, once again we do simulations of muon showers, and see what the unvetoed to vetoed rate from the Monte Carlo is. And then from our data, we just normalize it with the counts of vetoed single nuclear recoils. So this is in coincidence with muons. And then there's a correction for efficiency and exposure, and then you get that number over there, which is also pretty small. Okay. So we're ready to freeze the analysis because we have everything in place. That was the raw exposure we had. We set all our cuts, and we know our surface event background is a dominant part of our background, and it's sitting at about 0.6 plus minus 0.1. There's a systematic error that we believe is about the same size as the statistical, so we haven't computed it rigorously at this point yet. The neutron background is pretty small. It's less than, it's about 1/10 of an event. Okay, and so now what we can do is we can look at our expected sensitivity, and what we plot over here in the red dotted and the black dotted lines are median expected sensitivities. So with our background models, we can do a Monte Carlo and then say we want the result which is 50% of the way between the worst and the best result, right? Now the red one is just this exposure, and the black one would combine this expected sensitivity with our past results. And let's see what else is interesting over here. And this was our previous result at that point. Okay. So we're ready. We go ahead and open the box. So first, we lift the mask and look at the events failing the timing cut. So we get these counts. So these are events that pass the timing cut are candidate events. The ones that fail are not, and we see 150 of them, and that's consistent with our expectations. Then we go ahead and apply the timing cut, and here's what we get. We see 2 events. Okay, so what do we do now? We go ahead and compute limits and all that kind of stuff as usual. What ends up happening is because we have 2 events, we don't background subtract them. We actually include them, and so we land up with these limits with these kinks over here. Note that this is not as good as our expected sensitivity, and that's because we observe events. In comparison, we have other results. So let's see. This was the previous CDMS results. So we've done better. We still have the world leading limit in this region above 45 keV, 45 GeV. And in comparison, we have over here the orange line is xenon 10. And again, once again, the shaded regions are theory preferred regions, including, I think on this plot we also have a Kaluza-Klein model. Okay, We can also do some other things. So that was a spin-independent component of the interaction. So that was a spin-independent result. So we can also set a limit on the spin-dependent coupling. So that's what we end up getting. Competitive, but not excluding any new parameter space. Now this is interesting. So as most of you probably know, DAMA has claimed a WIMP or dark matter signal. And in order to reconcile DAMA's observation with null observations in practically every other experiment, theorists have proposed interesting models for dark matter. And one of them is this inelastic dark matter model where an interaction of dark matter particle with your detectors would occur only if there's enough energy for the WIMP particle to jump straight into an excited state. And so there's a cutoff now. And what ends up happening as a result is that instead of having that exponential spectrum, you would see a bump. And so now you can set limits in what is actually a three-dimensional space. So you have WIMP mass. Imagine cross-section going out of the screen, and this mass splitting, which sets the scale for this excitation. And it turns out we rule out most of that too. What you're seeing over here, though, is like all the cross-section is all suppressed in the sense that this is just a projection of all the region that we've excluded. Yeah.
So the unshaded area is the one that's still allowed?
Yeah, that is the only allowed region as of now, yeah. The black hatch mark is CDMS, and Xenon 10 excludes the red region. Okay, and both of these were actually computed by us. All right, so now we can actually look at the candidates and ask interesting questions about them. So we did observe two events. This is what they look like. So this is the ionization yield versus energy plot, and you see this guy sitting right over here in T1Z5. T1Z5 refers to the detector number, tower 1 zip 5. So that's the event over there, and T3Z4 is this event over here. Put in another viewing scheme, we can look at the yield versus timing. This is normalized to make the detectors comparable. And we see that, so this is the acceptance box for the two detectors, and this is where the events land up. Now these blue histograms give the neutron density, so that's for comparison to see what the WIMP distribution would look like if we had that many WIMPs. And okay, so those are the two events in those views. We go and ask questions like, well, were the detectors working properly? Of course they were. Any special conditions? No. Was the data quality all airtight? Yes, it was. Was the veto performing properly? Yes. So we go through this list and say, well, mostly things were okay. Essentially ideal running conditions, several months apart, and in different detectors. So these things look good. But then we come to this issue over here, which is we're scrutinizing these events pretty carefully, and we ask the question, well, okay, let's look at the traces. Now, this is unfiltered traces, so this is hard to do by eye. But somebody said, well, look at that trace. Could it have been jiggled around a little bit? Remember, that would change the timing information. So the placement of the pulse on the placement of the fitted pulse on the raw pulse can move you in or out of the surface event rejection cut, possibly. So we looked at this closely, and it turned out that we realized that our optimal filter scheme has some problems with events that have ionization energy of less than 6 keV, and a small fraction of such events. What ends up happening is we actually employ an approximation in our chi-square fitting scheme where we don't actually look for the minimum chi-squared. We instead try to maximize the amplitude. Statistically, as many of you know, it's approximately the same, except I guess we've gotten in this regime now where we've come up with at least one case where the fitted start time could have been, in a slightly different bin, and you may or may not have moved this event out of the surface event cut. This problem is not observed with the T1Z5 event. It's observed, sorry, did I say that right? Yeah, okay, yeah. T1Z5 event is fine. T3Z4 event is the one that looks like it may have a misreconstructed start time. But we'd actually have to go and reprocess the entire data because it's just a different algorithm. The timing cuts may be set slightly differently, and so it's a whole reprocessing that you have to do to investigate that issue. But anyway, so this is maybe suspicious, but anyway, but after realizing this issue, we went back and re-estimated a surface event background and added a contribution from this kind of effect. And so it was 0.6 plus minus 0.1, recall? And now it's about 0.8 plus minus 0.1. And now we've done Monte Carlos and stuff, and we can also assign a systematic error of about 0.2. Okay, so given this surface background estimate and the neutron background estimate we had, we can make this kind of statement which says that the probability of observing at least two background events, is 23%. That's not an insignificant number, so we have to conclude that these results cannot be interpreted as significant evidence for WIMP interactions. Okay, what else can we do? We can go back and look at a surface event cut. Did we make any mistakes setting the cut? And it seems like we probably actually didn't. So here's a way to look at it. So here on the horizontal axis, we have the predicted number of surface events that leak through. So predicted surface event leakage, and then you have the limit over here. And so the limit as a function, this is a curve that I've shown you earlier, and the red curve. And so you see the sensitivity as a function of how you set your cuts and how much leakage you would have allowed in. And we note that the events follow really well, except you see these two events over here that jump away from the curve, and then you resume. So our belief is that we did things right, we just got unlucky over here. And you also observe that if you move the cut around a little bit, you'd have to move quite a bit to go down to 0 events or to go up to 3 events from the 2 that we observed. So our result is actually not overly sensitive to the cut position. Okay, now's the new stuff. So we had a blind analysis, but now we're not blind anymore, and so we have access to the full distributions of events that we observe in yield, energy, and timing. And so we can do likelihood studies, and we can construct nuclear recoil and surface event hypotheses likelihoods using the distributions for the 2 candidate events. Now remember, this is low statistics regime, so you want to be careful, and you want to actually try different methods and use them as checks of systematics against each other. So we employ 3 different techniques. We do a kernel density estimate. So this is just looking at the surface event distribution or the nuclear recoil distribution and using no fits, but using a kernel density estimator in energy, yield, and timing, and in this energy range. And we do 2 other fitting schemes in which we use these generalized lambda distributions, which are great fitting tools and kind of conform to whatever data you have. And we do them in yield and timing in a 5 to 20 kV bin, and yield and 2 different timing parameters in a 10 to 30 kV. So this is all by way of doing cross checks. Okay, so now one has to be careful about what kind of questions you ask and whether they statistically make sense. And the problem is, depending on what kind of question you ask, the answer may mislead you. So after thinking a lot about that, there's a set of questions we came up with, which we thought were interesting to ask. The first is, what is the probability that at least one of the observed surface events is more nuclear recoil-like than the candidates in these detectors? And we see that so these are kind of the numbers you see: 24, 12, 12, 4, 5, 5 for the events, and we see that it's for T1Z5 for the event that actually did not have the reconstruction problem. We seem like we're actually close to the background distribution. Okay, then we can ask a couple of other questions, which is, if we restrict ourselves only to that box now and look at these likelihood distributions only in the box, we can ask questions like, how close were we to the cuts? And so we can ask, what is the probability that a random nuclear recoil is as close to the cut boundaries as the observed events? And so these are small numbers for T1Z5, and to be a true nuclear recoil or a WIMP candidate, the expectation value for that number is maybe about 50%, right? Being in the middle. Or you can also turn the question the other way around and ask, can you get a random electron recoil worse than the candidates that we got? And the answer is yes, you can. So 83%, 28% in T1Z5, and actually a pretty significant number in T3Z4 as well. So we conclude from the likelihoods that the initial calculation that suggested this was likely background is true. The nuclear so let me just okay. So the results verify the initial calculation that the probability of observing two surface backgrounds appearing as nuclear recoil is low. So the probability is low, but not significantly low. Okay, and of course they incur suspicion that these are actually background events. All right. So that's kind of the conclusion of the analysis bit. And so let me take the final few minutes to talk about the future CDMS plans. So CDMS-II, our target exposure was acquired, and we processed all of it, and this is the analysis that I just showed you guys. So what we're doing in the future now is we're upgrading to a 15 kilogram germanium experiment called Super CDMS, which will be operated at Sudan. And if this is our current reach, we hope to get to about here with Super CDMS Sudan. We have new improved detectors with better phonon sensor layout, and they're thicker. They were 1 centimeter thick in the past in CDMS-II, and they're 1 inch thick now. So that's a factor of 2.5 over there. And this is what a CDMS-II tower schematically would look like compared to super tower. So more mass, more exposure, that's good. In the future, we want to move to Snow Lab, to a deeper site, employ 100 kilograms of germanium, and that would start getting us into the Zeptobarn regime. Okay, real quickly, in the meanwhile, we're also doing a lot of detector R&D, and this is our newest detector, IZIP. Don't tell Steve Jobs. So the idea over here is that we have interleaved electrodes and phonon sensors on both sides. So instead of patterning only on one side, we pattern on both sides. The interleaved helps us with this. We can alternately bias rails of interleaved electrodes in a manner that surface events would see a different kind of field than bulk events. And what ends up happening then is that if you're close enough to the surface with these alternatingly biased rails, you would collect all the electrons and holes over here, and you would see a surface signal separate from a bulk signal. An event happening in the middle would actually just go on as usual, as it would in CDMS-II. And this ionization-based rejection over here alone is 10 times better than all CDMS-II rejection. And so this is not even talking about phonon sensor improvements. And actually, two-sided phonon sensing will allow us better timing construction, because we can actually look at the time of flight better. So this guy looks very promising, and our hope is eventually to deploy him at Dusel in a 1.5 ton experiment. Maybe the phonon sensing technology might change. Really, the challenges with this kind of experiment are no longer background rejection, because these detectors look pretty good. It's the engineering. So more of the R&D in the next few years will go into multiplexing and those kinds of things. And so that's what our future plans look like. And I will leave you with a summary. I presented the current analysis. We observed 2 events. The 2 events are likely background. And we hope to keep expanding CDMS. And new results are on their way. There are a lot of interesting experiments using different kinds of technologies in this field, and so stay tuned. So I'll leave it at that. Questions? Yes, sir.
The detectors are anisotropic with regard to efficiency. They're towers.
What do you mean by isotropically sensitive?
Let's say I had a stream of lips.
Yeah.
And so I rotate the detector. Do I get a different efficiency for detecting them? And I think you see, where do you calculate that effect, and how do you do it?
I want to say there should be an effect because of that. So we should be isotropically sensitive. Off the top of my head, I can't think of any reason we would see an efficiency difference, unless you guys have, yeah, for WIMPs. Right, so you can do some interesting physics with these detectors because we know the crystal orientations. We can actually also try to detect axions because of the Bragg scattering effect. And so there are some results we've put out based on that too. And that's where the orientation matters. Yeah?
Before you did this wrong, you must have, there was a possibility you could have gotten 10 or 20 of them. So I was just wondering how far your collaboration got into the thinking what criterion you would have before pronouncing an actual.
Right, so 10 or 20 events though was very unlikely because remember the exposure of this was just like twice the previous exposure, so that was very unlikely. But yeah, before unblinding, we lay out criterion for ourselves, saying okay that if you know what it means if it's 2 events, what it means if it's 3 or 4 events, and really it starts getting significant for this particular result only if it was 4 events or more.
5, what would have happened?
5 is probably also consistent with the null observation that we had in the past, but beyond that, we just screwed up.
Never would have, we knew you weren't going to announce the detection.
Well, I mean, it was very, very unlikely that we would see that many events to begin with. Yeah. Other questions? Yeah, Mansi.
So is there any particular, what I'm trying to understand is that for this to be, to claim this as a wind detection, could you take position somewhere differently on your yield timing plots, or is it just an end problem, like 2 is 2? Or could you have slightly different characteristics which would be far enough from the properties of rain, or is there some other characteristic that would distinguish it from?
It's a combination of several things. The count problem is one thing. 2 is very consistent with the background model in terms of counts alone. In terms of likelihoods, yeah, you can engineer a situation where your events were smack in the middle of the acceptance region, and you said, oh wait, this looks very WIMP-like. True.
When you were unblinding the box, it looked like there was a third near to your detection region. Have you followed that one up at all?
So okay, so you're talking about the near missed event. So there are actually 2 right over there. They're almost, yeah, there are 2 over there that overlap. They're in two different detectors again, and yeah, they just missed the signal region. There's nothing special about them.
Have you looked at them using the likelihood?
No, we haven't gotten around to doing that yet. No. Any other questions? Okay, thanks.